Okay. So, good afternoon, everybody. I would like to thank you, our panelists and the moderator, by the acceptance of this invitation to have our second webinar from our chapter, IEEE has chapter from Brazil. So we are really happy to have this webinar today, and I will give the words to Marcelo to start the show. Thank you, Marcelo, and thank you, everybody.
Thank you, Paulo. Thank you, everyone that is watching our webinar today. And I prepared a short presentation just to give you an overview about what we are going to talk about. Okay, it's just 1 second here. Okay, I think you already can see this. So the idea of this webinar is to show you what's next on agricultural robotics. Okay, for sure, in Brazil, agriculture is a very important thing. Agribusiness is really, really important thing. We can see checking these numbers. So millions of tons of grains and billions and trillions of reais and dollars. So it's really a big business. But not only because of this, we decided to have this talk about agricultural robotics. It's because we have a huge population growth. So today we are around 7.9 billion inhabitants in Earth. And in 2050, we are going to be almost 10 billion people. And we need to feed all these people. If 5 years ago we had around 800 million people that couldn't get enough nutrients to have a good life, today the situation is much worse. So we need to work on this. And for sure, according to ONU, United Nations, and FAO, we need to increase our food production. They said around 70% until 2050. But we should remember that increasing production doesn't mean to increase the production area. We need to increase the productivity. And we need to take into account climate change and environmental issues. Okay. So one good idea is to use robots. In our lab at USP in São Carlos, we work on this field. And we have many robots there. Some we built, some we bought. But we know that it's not easy to deal with these situations because we are talking about field robotics. And it's really tough to deal with many problems that we find on the fields. Okay, so what's next on agricultural robotics? We have to face this challenge: environment, perception, real-time response, sometimes autonomy, costs, and etc. And because of that, we invite this great research around the world to help us to have an overview what is up, what's next, and how we can deal with this. So thank you for accepting our invitation, Professors Olivier and Hugo, Professor Gires from the US, and Professor José Paulo Molin from ESALC at USP in Piracicaba. And I would like to hear from Professor Molin his views and the needs that we need to deal with now. Thank you, and welcome.
Okay, hello everyone. Thanks Professor Marcelo and Professor Paulo for the invitation and for the opportunity for us to give some brief ideas about or our point of view about what is going on and perspectives for the future on robotics in our agriculture. I've not spent time talking about the rest of the world because we are very well represented by colleagues from Europe, especially. That is the place that things are going on. So let's talk about the Brazilian point of view. Um, we, I will start saying that we have, for robotics, we have at least two major demands or two major applications. One, the operations, the production front, and the other major application is monitoring and so collecting data, all kind of data. Okay, going to the first, that is the production or the operations. I would say gradually replacing the standard mechanization. We have to consider that in Brazil we have it as anywhere else, but in Brazil is very clear for us. We have two major kinds of agriculture. The intensive and specialty crops agriculture related to small meat farming, and the commodities production related to, I would say, mid-large operations. Back to the first level, the small meat farming, still running on manual and some mechanized activities, and to the other sector that is the major production area of Brazil, talking about soybean, maize, cotton, sugarcane, orange, coffee. On those, I listed our major exporting products. Farmers are still in the movement of enlarging their machines. We have a very strong local industry supported by local manufacturers and by the three major global brands of ag machinery, and they are still trying to supply big machines every day, every year, bigger and bigger, because the operations are high power demanding operations. So we're talking about basically we are running on no-till conditions in Brazil. So soil tillage is not the major demand anymore. Talking about power, we are talking about seeding, planting, spraying and harvesting, basically. Okay, so if we go to the market, we can note that our tractors are still getting bigger in terms of power. Our harvesters combines are still getting larger every year. So that is not the situation where we can talk about totally robot or the hard application of robotics yet. In that part of the market, we see the movement growing faster, I could say, in terms of getting autonomous vehicles, not with much intelligence yet. The reason for that is because as I told, our industry is still trying to keep their projects and their products that are on the shelf, talking about tractors and combines especially. Autonomous vehicles, they come as a request from farmers gradually, and the reason is clear. They are trying to replace or to decrease the amount of labor on their farming operations. That is one part, and we can get back back on that if we still have time. Now let's talk about the second great application, that is the monitoring and data collection. Okay, we're talking about intensification of agriculture. Marcelo just mentioned the big numbers. Yes, we have to intensify, and the only way to intensify our agriculture, our tropical agriculture, is by adding efficiency to the process. So we have to intensify in terms of getting the specific site-specific treatments for any piece of land, and that is done by more and more data from previous season, data from the present situation, and some estimation from the future, especially on climate. So small robots on land or from the air to collect data is the major issues for the next few years. But robot is part of the business, and we have to deal about the other part of the business, that is the sensors, to collect good data. We are seeing a good movement in the direction of robots, but not that much in terms of sensors. And we are talking about sensors, crop and soil sensors, basically. We are on tropical soils, normally poor soils in terms of soil fertility, and we have to deal about nutrient replacement. Just mentioned that we import a lot of fertilizer. So yes, we need a lot of effort on monitoring, collecting data, making intelligent solutions for diagnosis and for interventions in terms of site-specific applications. So that is our point of view, and yes, we have a lot to say about that, but we are limited on time. Well, Marcelo, thank you, and I'll keep open for
thank you,
questions.
I have some questions for you. One big question that pops in my mind always when we are talking to farmers is that, in your opinion, do they feel comfortable when we say that we are developing a robot to help them, or this word robot scares them a little bit? What is your opinion about this?
We have any kind of reaction that you can imagine from A to Z, because we still have farmers that let's mention one thing that is important, at least for our colleagues from outside, we have to have an idea. We are just finishing the mechanical harvesting of sugarcane in Brazil. Entering to the finishing the process of mechanization of harvesting sugarcane. We are not on the harvesting of orange yet. Orange, we are the largest orange juice exporter in the world, and is not mechanized yet. Nothing, okay, for industry, orange for industry. And coffee, for example, we are in the middle between mechanized and hand harvested. So we have a entire point of view in terms of opinions and reactions. But the other day I saw a organization from soybean producers in the Midwest of Brazil saying that they are hiring some kind of solution for robots for spraying. They want to have their robot for spraying. They have their reasons for that. So yes, we have people open for with open mind for robots, and we have people that still don't understand what we are talking about.
Okay, that's great. And so now I would like to ask our colleagues from France so they can tell us something about the situation in France and Europe. Please, Olivier and Hugo.
Thanks a lot, Marcello, for for this invitation. Just a few seconds, I have some slides, so let me share them. Okay. So I'm not sure it's okay. Okay. So yeah, I am Olivier Lee, and my colleague Hugo Gimbert is presenting with me. We are from Bordeaux in France, in the southwest of France, and we are from the Robot team in the Labri, the French laboratory of computer science, and we have a robotic team. And one of our activity is agricultural robotics. So we'll talk about what we are doing currently in this area, and that's it. So let me. Does it work? I'm not sure. Yeah. So we came to agricultural robotics a few years ago now by designing agricultural autonomous robots. At first, we was interested in particular in reducing costs of agricultural robots, and one of the targets we had at this point was to reduce the cost of GPS, actually, scientific GPS, which is essential in a lot of agricultural applications. So we experimented at this time the single frequency GPS. We experimented that on two machines that we designed for this occasion. The first was a trellising post planting machine in the vineyard here in Bordeaux. And the second was an automatic plantation machine for poplar, which is currently in exploitation, actually, but not with the single frequency GPS. So we have this experience of doing full machine. We do full integration of machine, and they are in exploitation. We have in mind to use them in the real agricultural life. It's very important for us. However, experiments in single frequency GPS are difficult because of the launching phase, which is long, and so at the moment we use double frequency. We still use double frequency. But okay, these projects are past now, and we are focused now on weeding, and in particular in organic culture. And maybe I will pass the speak to Hugo to speak about that here. Yeah.
Thank you, Olivier. Thanks for the opportunity to present our work. So something which might be specific to the French agriculture with respect to the context in Brazil is the huge development of organic farming in France. And it clearly creates new challenges. This is the national policy to drastically reduce the use of chemicals in agriculture before 2025, and even to stop and the use of glyphosate this year in 2020. So it means that more and more tasks should be in the short term handmade, For sure, it's a remechanization process of agriculture, because organic farming means less chemicals or no chemicals. And another thing which is specific to the French context is that the cost of labor is very high. So, yeah. Is there a question, or I've seen a question popping up?
Yeah, we can check the questions after your presentation, no problem.
Okay, good. Yeah, the cost of labor is very high. So clearly, going back to a manual agriculture is not possible. So this is really a strong incentive for agricultural robotics, for the development, and the French government is injecting money, and there are programs to develop it. Olivier, can you switch to the next slide, please? That was the first project. We designed a weeding machine, which is aggregating visual information, so detection of rows by color camera, and also centimetric GPS information, so that we can weed first time based on the vision system, and then if there are further weeding phases later on, and the visual conditions are bad because the plants are very high or there are too much adventices, then we can use the GPS the second time. Can you switch to the next slide, please? Olivier, can you? Yeah. It doesn't work? Okay. Yeah, and I want to spend more time on this project because this is a project we are working these days. The project is to be able to mechanically weed in the rows. It's intra-row weeding, so we are weeding between the plants, not just between the rows, but between the plants themselves. So for that, we need high precision. We use a vision system which is able to discriminate between the crops and the adventices. So it's using neural networks. And the challenge is, of course, to detect, distinguish between crops and adventices, but then also the action, being able to precisely have an action which is at this precision. It's like the other magnitude is centimetric precision of the action of the tools is quite a challenge, actually, because we are moving at the same time and the ground is not flat, and it appears that even if you are moving at quite low speeds, like 1 meter per second, having centimetric precision is it means in terms of time to have hundreds of seconds precision in the control chain, in the detection and action chain pipeline, which is not so easy to do. Yeah. And can you move to the next slide, Olivier? And to get this precision, somehow a game changer is that we have our own platform, which is an electric tractor, which is able to operate at low speeds, which may be funny, but it's not so easy to operate at low speeds on a conventional tractor. So we are very happy with this electrical tractor, which is autonomous, so it's not a problem. We can let it work for hours without an operator, and even if it's quite slow, even if it's moving below 1 meter per second, economically it's tractable because there are no operator involved, so no salary to pay. Plus, the navigation is very precise. It's actually much more precise than what you can get with a human operator really driving a real conventional tractor. Is my time over? I guess it's...
Well, if you can finish presentation, no problem.
Okay. So as a conclusion, what I want to say is with those projects, we are between research and industry. We are actually, it's almost state-of-the-art techniques that we are using. And the challenge is to find solutions which are also economically tractable for the companies we are working with. And at least in France, it's a it's a challenge because even with a strong political incentive, it's not so easy to go from the lab to the product. And still, that's our ambition. And we have actually started to selling those this e-tract to research centers, not only ours but other centers. And we would like someday to see them in the fields in France by dozens, and we'll see if it happens someday. Yeah. So I see that there are questions. So yeah, Marcelo. Yes.
Okay, so we have some questions for Professor Olivier and Professor Hugo. The first question from the audience is this. We have a tendency, at least in Brazil, of huge agricultural machines, but they are not well designed to small farmers. The case of Europe, but also Brazil. Do you think the robots will allow to move in other direction? Small autonomous machines, for instance?
Hugo, or
what I know is that there are projects, and there are actually actual large tractors which are autonomous. I think in the US it's used. Probably in France there is a need for small robots, small in terms of size, because we have small farms, especially for vegetables. Also in terms of cost, because not every farmer can afford a huge tractor. Also, something else that I want to say, that quite often, at least in France, the startups, the innovating in agricultural robotics, they like small robots because it's easier to handle, simply. It's easier to design, to test, to experiment, and it's easier to launch a project with small robots rather than large robots. So in France, clearly the trend is to small robots for these different reasons.
there is also, maybe I can add a reason for small robots, which has some importance, at least in France, is that the small robots pushes less the soil and are reputed to be better for the soil health. I mean, in terms of organic culture. So there is also a convergence of several arguments for small robots.
Okay, another question is robotics being used in controlled environment agriculture as well, or it is, or is its viability only relevant today in an open field agriculture context?
Well, maybe I can answer first, and then Olivier, you. The most controlled environment agriculture these days is clearly what is called vertical farming, which is this really revolutionary way of doing some farming in the core of the cities by stacking the plants one above each other. So here clearly it relies a lot on robotics to make the various tasks automatic. Not anymore mobile robots, clearly, because it's no more in the fields, but still autonomous control of the vertical farming, and autonomous mechanical operations are in the core of vertical farming.
No, I think.
Okay. So the next question is about the robot that you showed, A-Tract. Is it full autonomous?
Yes, it can be programmed to follow either path, geolocalized path, or to follow rows based on color analysis, or also to follow the ground based on its shape. So, for example, if you plant on what in French is called a butte, I don't know what it's called in English, but on some
small E.
Sorry?
No,
yeah.
no. I don't know
it can
the word.
follow shapes also on the ground. Yeah, and of course you can also take manual control if you need. For example, to have it down the transport platform, we need to do it manually. It cannot do it automatically yet.
And of course, it's autonomous for energy as well.
Yeah.
It embeds the battery and.
Okay. And another question here. Are robots a viable alternative to chemical pesticides, even in large areas?
So first, when it comes to weed control, I would say clearly the answer is yes. And it's just a matter of technical gap to perform. But pesticides, of course, is not only about weed control, and clearly there are challenges about moisture control in vineyards, for example, or insect control that are not yet for which there are not yet any viable robots alternatives to my knowledge.
Okay, another one. Do you think that European countries can help to scale up the production of robots to help agriculture? Is there some kind of incentive to do this?
Olivier, you are in this European program, no?
Yeah, I'm not sure. On the
there is this European program to design competitions between agricultural robots. The second project that I did present to you is actually there are 4 labs working on 4 projects for the same purpose, and we are competing with each other, and it's very stimulating. And there are European efforts to be able to assess the performances of agricultural robots and being able to somehow tell objectively what is working or what is not working yet. And I think this is important for the development of European agricultural robotics. I'm not sure I really answered the question, but
And I would say the last one now. Do you believe that the 5G will help us to deal with this big data and try to solve this perception and detection and all these things in real time?
Uh, 5G? For what I know and I practice, I don't believe that when it comes to real-time agricultural robotics, you can really externalize the computation to some remote computer. So I would say 5G, to my opinion, is not a game changer because you still need to embed the computation, the controller, and everything, and you cannot rely on a network except for geolocalization. To get the work done. So I don't expect this to be a game changer, but of course, maybe I'm wrong, right?
Okay, thank you, Olivier. Thank you, Hugo. And now we will call, I will invite Professor Gilles choose
Hi.
here so we can.
Hi.
Hi, Jish.
Hi. Let me try to share my screen. Okay, so the only way to do is the whole screen, I guess. Give me 1 second. Okay, so I will share my screen and are you able to see my screen, the whole screen?
Yes, perfect.
Okay, great. So thank you very much for inviting me, Marcelo, and all the other experts from the world. This is really a great pleasure to say a little bit more about the kind of work we're doing at the University of Urbana-Champaign. I'm Girish. I am the Associate Professor of Ag and Bioengineering and Computer Science at UIUC. And I'm going to talk about some of the work that we've done. So as you know, we're here in Midwest in Illinois. There's a very large acreage of corn and soybean, and similarly in most of the Midwest, as Nebraska, Kansas, Iowa, Indiana, we basically live in what many people nowadays call a corn and soybean desert. Right, so most of the acreage we just plant with these large equipment, and that's leading to a lot of problems. So you probably heard about nitrogen in the seas and pesticides in your food, but one of the key problems that's really becoming noticeable is the rise of herbicide resistance weeds. So these weeds are not controlled by known chemicals, and they're really affecting not only the bottom lines, but also overall questioning the sustainability of the practices that we're using today. And of course, as you know, on the other side of the world, in India and in Africa and in many parts of Asia, a lot of the work is done by human labor, and that's also not very sustainable, and in some ways can be very exploitative. So overall, if you look at the Midwest and the United States specifically, you see that the cost, the money that the farmers take back home has been consistently declining because there's a lot of pressure from the top on the commodities, like, you know, corn and soybean basically gets traded on the commodity market, and a lot of pressure from the bottom on what they need to, how much money they need to invest in order to run a profitable business. So if you look at this chart from USDA, you see that even as the cost of labor and land have been declining over time, the cost of inputs, intermediate goods, so fuel, chemicals, have all been increasing and have actually now surpassed the cost of tractors. But that's also kind of, you know, have been having this this trend. So the work that my group does, and also the Center for Digital Agriculture, we recently got an AI Farms Institute, that, and then the company that I co-founded, EarthSense, we all believe that robotics and AI will make farming sustainable and profitable. And our overall idea, this is just a cartoon, is that there will be small robots, the teams of small robots in fields that can scale up and down. And I think we've already touched upon that idea with other people. But I think what's interesting is the path that we would like to explore from our research program. And our path, we feel, starts at the seeds. So really helping make better seeds for agriculture, because seeds is where a lot of the program for the farming is. And then from there, go to fewer chemicals, which is obviously a much more broader problem, but also really difficult to tackle. And then finally, move from there to diversified agriculture and fully productive ecosystems. So I'll talk a little bit about the seeds angle, because that's something that people often miss, and I missed it, honestly. And I learned about it from Steve Long and Carl Bernanke and some great crop scientists, and I'd like to share that. It's also very appropriate because we are being hosted by a Brazilian organization today, thanks to Marcelo. And as we know, corn, which is the dominant crop in basically most of Midwestern United States, is actually not natural. Not only is it not natural to this geography, but it's bred from this plant, teosinte, by ancient Americans who bred it 9,000 years ago with different plants, and 3,000 years ago we have modern varieties of corn coming up. So this breeding process is really at the root of agriculture. And in the United States and maybe Brazil and Europe, we have seeds that are bred for that environment. But when you go to Africa and Asia, you see often that the yields are twice or four times as less, but the population is really increasing. So to deal with this, the scientists are trying to solve the genome-wide association problems. So they're looking at which genes are responsible for which phenotypes, which could be crop physiology phenotypes like plant growth, plant height, plant stem width, plant leaf area. And for this, they run these massive trials in which in this 40-acre plot, you see these different varieties of sorghum are planted next to each other in a 3 by 3 meter grid. And they're trying to compare these and measure this. And measuring this has become a huge bottleneck because most of the measurements are manual and they take time and sometimes they're not very accurate at all. So what we've been doing is creating a robotic system that can go under the canopy, because a lot of these measurements are really close to the plant. You have to get under the canopy to get them. And then creating the AI that will take those measurements and give the plant breeders a quantitative result. So this is the robot TerraSentia that we've built. We have built at this point. We've made over I think like about 90 of them. This year we made 45 of these robots. It can go through rows using without GPS. And then the other part of what we've done is the AI that takes this data, the vision and the LiDAR and all kinds of other data that we collect, and converts it into quantitative measures. So before you were looking at stem width, then you were looking at ear count. And here we're looking at 3D reconstruction of crops. And then this information is basically then given to the crop scientists. So there's several things that we've learned along the way. One of the things that we've learned is the power of the small. So we made this small robot, and it's inspired by drones that fly in the air. And a lot of people were like, it's never going to work in field conditions. But we learned a lot about how far we've gotten with manufacturing techniques, with brushless DC motors, and robustness of computers, that we realized that you can actually make really small, low-cost robots that are superiorly ruggedized. So here's some examples of this robot basically driving through snow, driving through really dry and muddy or clumpy terrain, driving in the evening, driving in, of course, in tree crops. So we also found that this small form factor really opens a lot of doors, because not only can you get in the canopy of corn and soybean, but you can get really close to grapes. You can get through grass. You can go in tree crops, and most interestingly, you can actually make it extremely portable. So here, this is now in India. And you can see that it's really easy to transport the robot. And so these types of robots, when you attach them with implements, could potentially serve as the new unit of work that can scale up and down. And it still remains to be seen whether this is big enough, right? I mean, for certain tasks, you might need the E-Track type tractor that we saw, but there may be tasks that could be done at this form factor. And if you do it, it might be really interesting, because the flexibility and the cost of making small robots is, of course, comparable to that of making computers. And you can really crank a lot of these out at really low costs. The other thing that's good with the small form factor is not only can you bring the cost down, because if you want to impact commodity agriculture, you need to be bringing costs down to about $50 an acre. But you can accelerate really fast the levels of autonomy, right? So we talk quite a bit about autonomy. And recently, with a couple of my colleagues, Katie Campbell, Drix Campbell from University of Illinois, and Chinmay Soman from EarthSense, we got together and we kind of came up with levels of autonomy for agricultural robots that are a little bit more user-oriented, rather than capability oriented. So, robots can follow waypoints, but does it really get a user off the ground? So we believe that these are the 5 levels of autonomy. They're very similar to the car levels, but they're different because there's the one-to-many interaction. So level 1, which is where most autonomous robots seem to be, is hands-off, which is the robot can drive itself, but somebody still needs to take control if something goes wrong, or if the robot has to do something that's not in the program. So that still does not get the person off the field. The second is eyes off. So you no longer have to visually follow the robot, but you still need to be close by because it might still get into a situation where you still need to rescue it. And here, the time between intervention needs to be about 50 minutes. The third, which is, I would say, the minimum value proposition or the minimum viable product for most of these robotic platforms that we were talking about, the French one that we saw, and many other ones, is really the mind of that you can get one person to control many robots, and maybe that person's at the edge of the field, and that's similar to what farmers do today. They're in the tractor, so that it's okay. They can still be at the field, but there's many of these robots together working. And then really where you start adding the value and what people are waiting for is not being at the site. So monitoring off-site. But for that, I think, we need to be really bringing autonomy to a level where a lot of the AI is on the robot and can take a lot of these decisions about what to do in contingency. So that's the path that we would like to go. And Marcelo, do I have more time or am I running? Okay.
Oh, sorry. My microphone was off. You have 6 more minutes.
Okay, great. Perfect. Yeah. So now I'll just give you some updates on the work we've been doing this summer. A little bit of that is with some of the students that Marcelo also advises. So we have this autonomous farm that we've set up at the University of Illinois, and we've been moving towards level 2 autonomy. So by level 2, again, we mean that eyes off. So we require the robot to basically make a decision on which sensor package it's going to use. So before it was using LiDAR as it was driving through the row, then it switched to GPS, then it's making the maneuver, and now it's going to switch back to using LiDAR. But we also talk about adding AI on top so that if it makes a mistake, because it will eventually, these robots, as anybody who works in robotics and specifically in field robotics knows that all the assumptions you make are wrong. So sometimes at some point it will make a mistake. And at that point, we've been adding AI to detect the mistake that it's making and then recover from that mistake. So that's one thing. The second thing that we've been working on is getting these robots to work together. So here's an example of 3 of them driving autonomously in the row following mode in corn. They're not really talking to each other right now, but their speed is kind of happens to be the same. So they're synchronized from that sense. And then also getting the robots to work in the day and in the night. And finally, this is something really exciting. A lot of our work, this is with Professor Saurabh Gupta and my student Arun, is trying to increase the speeds of the robot. And one of the things, so this is running at 3.5 miles per hour now. And one of the things we found that actually to increase the speed of the robot, we have to move away from LiDAR and move to machine vision. So it's using machine vision in this case, driving through the field at a pretty high speed, in combining vision and inertial data to do these maneuvers. And then the other thing that we're working on is actually improving the dexterity of the robot. So right now, our equipment is kind of here. They can scale up. It can scale up the large equipment, but it doesn't have a lot of dexterity. And then human labor is here. It doesn't really scale up, but it is very dexterous. It can do a lot of different things. And the robots that we have, and I would say many ag robots actually, unfortunately, are here. They don't scale up yet, and they're also not very dexterous. So the scale problem, I think, can be solved with size and autonomy. But for dexterity, we need to be able to make some advances to the foundations of how we interact with plants. So in this project with Professor Girish Krishnan, we've been working on these modular grippers, these soft arm-based grippers that are inspired by octopus arms and elephant trunks, that have, again, compliant grippers. And we have this hybrid setup that where the grippers can extend out of this rigid arm, so that when you are near enough the berry and you can just reach it, you don't need to extend the arm. But when the berry is not in reach, you can extend the arm, and you can do hopefully a lot more complicated things that we'll be able to do in the next few months to grab the berry and thereby really leverage the benefits of both soft and rigid arms. So, just ending this, because this is about the future, I think I was just thinking about what is this cascade of things that have to happen. And I feel like the first is really the handling of the edge cases. Autonomy is only as good as the time it fails. So minimizing those edge cases, getting rid of them as much as we can, with learning, without learning, would be really good. Then increasing reliability of the whole system, which is very important and an underlooked thing in academia. Mostly we reward algorithms in robotics, but not so much the systems, which I feel really is changing and should change, because if we don't create systems, then there isn't any place for industry to start from. Then the reducing the cost, and that means using cheaper and cheaper sensors and creating better and better AI that can leverage those cheaper sensors. And then finally, we can go into problems in multi-agent coordination, human-robot interaction, and federated learning. So that's kind of the things that we're really hoping that the future will bring. So that's what I have.
Okay, Jirish, thank you very much for sharing with us the works that you are doing now and your point of view. I have some questions here for you from the audience. The first one is environmental availability, light, terrain, different crops, and so on, a challenge for agricultural robots? If yes, could you talk a little bit more about that? What are the biggest challenges, possible strategies for taking them?
Absolutely. I think they are a huge challenge. Agricultural variability is the reason we don't yet have robots in the field. And I think the way to approach them, again, is first and foremost reliable systems, which is something that we should all really invest time in as roboticists and as anybody else. I think there's a lot of value in making good, robust, compact systems. That's first. And because a lot of the problems can be dealt with by making, like, for example, if you can make a robot that can go through puddles, then you don't have to detect puddles. You can just go through them. If you can make a robot that can bump into the crop and not hurt the crop because it's lightweight or whatever other reasons, then you can be okay with accepting mistakes. If you try to take perfection to agricultural robotics, I think it's very difficult, because the environment is so different and so challenging that you can't really get out of it. So I really believe that the right system form factor matters a lot. And then the second answer to that is AI. And of course, AI that's based in learning seems to be very promising right now, as we're seeing a lot of deep learning based approaches. But I would caution there, though, because I think things like, while supervised learning is really strong and can be used and possibly has a lot of potential, there is still a lot of work left to be done before really interesting methods like reinforcement learning can become practical. But I would say that the biggest challenges and possible strategies would basically be thinking more about learning and spending more time on thinking about how the AI should come together for the robots on top.
Okay, thank you. And another question, this one's from Professor Paulo Drills. Is the project of this small robot open source? How about the price of each one of them?
Yeah, that's a very good question. It's not open source. So some of the software we might make open source over time, but the robots themselves are currently being manufactured by the company EarthSense, which is incubated at the University of Illinois. And you can talk to them. I think for academic, they have different pricing, but I think the overall goal is to bring the cost of the robot to be under $5,000 or less. That's the idea. But that's not where they are right now. I think they're closer to $15,000, $20,000, but that's kind of where it needs to go.
Okay, another one. This is from Hugo Gimbert. What limitation of LiDARs made you move to camera-based navigation?
Yeah, it's a very good question. So I think LiDARs overall are a great place to begin. So we began with LiDARs 2 years ago. We wrote a number of papers on it. It's beneficial because the data that you get is like 1070 dimensional vector. You can do a lot of things with that. But because the LiDAR reduces the information into just a point cloud, there's not a lot of other decisions you can make. Like if the LiDAR is occluded due to leaf or due to the stem, it's very difficult to tell which one it is. And then the cost of the LiDAR is also a lot more. I mean, even the cheaper ones that we have are around $1,500, $1,000. So compared to a camera, which can be $30 or less. So I think as you know, and it's well known in robotics, the problem with vision is that there is too much information. But with deep learning, there's ways to handle that now. So we feel that vision actually is a lot more promising from that perspective.
That's great. Another one. Could you talk a little bit more about the robot instrumentation? Any paper about the small robot, Terra-Sentia?
Yeah, absolutely. So 2018 Robotic Science and Systems Best Paper Award actually was the Terra-Sentia paper. It's an older version. It's a 3D printed robot, but the sensors are the same. So we have one LiDAR in the front, one LiDAR in the back, and one camera in the front, two cameras on the side, another one on top that's just for agronomic measurement, and then an embedded RTK, GPS and inertial sensor inside.
Oh, that's great. Another one. How Terra-Sentia deals with the rain irregularities?
Yeah.
Is it does it have some kind of controlled suspension system?
Yeah, it's a very good question. So it has a suspension system, but it's not controlled. And again, that goes back to the compact system thing that I said. I think one of our design ethos or design philosophy with Terra-Sentia was simplify the robot as much as you can. So we have only 4 motors. There's no steering. It turns skid to turn, and the suspensions are passive suspensions, but it's extremely rugged. So the weight to strength ratio is a lot more than some of the bigger tractors, I would say. So I mean, like some of our engineers stand on this robot and it drives with them. So it can really take like 160, 170 pounds of weight. So we feel that the irregularities are not, I mean, obviously if there's a giant ditch, it's going to fall into it. But in a regular field, it can basically just go over stuff.
Okay, so now another question. Can a small robot like yours be made multifunctional? For example, for weeding, etc. Can the same machine be used for this multiple purpose?
Yeah, I mean, I would hope so. I would hope that it's basically the same core and different clothes, right, for the robot. So it has a different attachment or a different body, but the electronics and the AI is similar. So yes.
Okay. Instrumentation, let me just check here. Girish, instrumentation in respect to soil and plants parameters. Does the robot have this kind of sensor?
So it has a camera which can be used, but it does not currently have a soil sensor. But that is a modular sensor that we hope to add at some point. So if anybody has a good that's one thing. So if anybody has a sensor that they would like to try with us on the robot, that's a collaboration that we're looking for right now. So we'd be very happy to give that a shot.
Okay, and the last question is about the United States government. Is your government somehow financing research and trying to scale up the production of robots for agriculture?
So I think the United States government supports significantly research, as you know. Recently, the government supported an AI institute, which is a $20 million. It's at the university, a $20 million institute for AI in agriculture. Two institutes were supported. One is at UC Davis, jointly supported by NSF and USDA, and the second is at University of Illinois at Urbana-Champaign. So this is just one example. We also have the National Robotics Initiative program that the government supports. This is through NSF. It's a multi-million-dollar program. And then the CPS, Cyber Physical Systems program, also through NSF, where people can submit competitive proposals to. Those proposals get a lot of attention, and typically it's very competitive to be able to get those awards. And of course, there's USDA. So there's a lot of federal funding for research. And then for small businesses, the government also supports small business initiatives and research, or SBIR program, which actually make a monetary grant to a business if they write a competitive proposal. It's a very competitive process, but it's there. On top of that, I think I wish we would do a little bit more on the sustainability angles, try to push that a little bit more. We really look, at least I personally look up to Europe at the way they handle their sustainability, and they handle some of the concerns about chemicals and things. I wish we would do a little bit more on that. But other than that, I think there's a great support from the government.
Okay, thank you, Gilles. And now I would like to hear your final remarks. So we are closing the webinar, and the first you, then our colleagues from France, and finally Professor Molin from Brazil.
Thank you.
Okay, Gilles, you can give us your final remarks.
Oh, so I thought Professor Molin was going to say. So my final remarks are that I think agriculture and robotics are a match made in heaven, in my opinion. I think we need this. Labor is a big challenge in agriculture. And I am very excited to see a lot of people being excited about it. I hope more young students choose to follow this path for their careers. And I think, a lot of people believe that autonomy is a big problem for our generation. And of course, we're seeing a lot of great work done in autonomous cars. But I think that it is more likely that we will have robots in fields before we have autonomous cars everywhere, because fields, even though they're varied and all that, there is some structure, right? There are the rows, and you can do things, you can rely on GPS, there's no people around. So I feel that there is a lot of potential in this problem, and it can be a big success story for us as scientists to really make this happen and address some of the sustainability and labor concerns.
Thank you. Olivia?
Well, I don't know exactly what I have to say, but well, there is here, at least in Europe, there is a big topic about organic food, and we are in this transition where we try to produce a big amount of organic food for everybody, and this challenge, I think this challenge will be achieved with agricultural robotics. I think there is no real other solution, and also with lightweight robotics. I mean, for the age of the soil. The robot of Karish are even ours are lightweight, and this is really the important trend. I think we have to follow. Thank you.
Yeah, your robot looks really beautiful, by the way, Olivier.
That's great. And now, Hugo, please.
Well, thank you. I don't have much to add. I would say that yes, lightweight robots are good, but when you go to real farmers, especially those having thousands of acres, they are very much used to heavy robots. So we have to really give proof that in real scenarios, in real use cases, we can do something, and that is a challenge.
Thank you. Now, Molin.
Yes, well, first of all, thank you again for this contribution. And that is the point that I want to stress. Agriculture is still, at least in our place, is still kind of self-sufficient. Agriculture is kind of self-sufficient. That means we are still not used to have contributions or multidisciplinary contributions to agriculture. So it's a revolution, and robotics is the most expressive part of that revolution. External contributions from multidisciplinary approaches to agriculture is not easy from inside to understand the movement, and we're in the middle of that movement now. Very, very grateful, and thanks for your contribution, because you are all from outside, and we are kind of the inside people, or the self-sufficient agriculture guys. Thank you very much.
Thank you, Molin. So we are almost ending here. I would like to thank all the professors and researchers that took part in this webinar. I would like to thank the audience that sent lots of messages, questions that we are going to send to the researchers too, and try to answer you. And it was a great pleasure. As you could see, it's a challenging area, full of things to be done. So we really need to work together and to solve these problems. And it's nice to see what is happening in Europe, in the US, and in Brazil. And I'm sure that together we can do a great job and help humankind to solve this big problem that we're going to have in a few years. We need to we need to feed our population. And this is very important for us to do it in a way that we do not damage the nature, we do not increase these climate change problems and so on. Okay, so thank you again. And don't forget, very soon we are going to have a new webinar, and stay with us. Bye-bye.